Okay, so welcome everyone. I'm Andrea from Politecnico University of Milan, and today I'm gonna talk about our recent result, an SoK on verifiable federated learning. So very quickly, just to recall on federated learning. So with this paradigm, we can basically train a model with many clients contributing on the training, and the objective is to keep private the data set in those use cases where, of course, the privacy of the data is important. So in specific use cases such as healthcare or finance, we can assume that the clients, the entities behave correctly, they don't cheat, but in the general case, federated learning can be used to train any kind of models. So in the general case, we don't have any guarantees that the parties behave correctly. Furthermore, since we have many participants to the protocol, also the attack surface increases. There are many attacks that are well mitigated. There are others that are somewhat mitigated. And this recent result in the box shows that it's also possible to plant backdoors without the possibility to discover them post hoc. So we and other people that works on this believe that verifiability can help in mitigate this kind of attacks. So just to give you an informal definition of verifiability, basically we have an executor that rather than running only the protocol, it has also to show, to send sort of an attestation of an evidence that the execution was performed correctly. So we have two main kind of technologies for verifiability. We have zero-knowledge based that are based on cryptographic assumptions, and we have trusted execution environment based that are based on hardware assumptions, producing a so-called quote. So in federated learning, the three steps where a client, where a participant can cheat are in the usage of data, in the training algorithm, and in the aggregation. So verifiability can be put into these steps to provide further, to make it less possible to cheat in these particular phases. So to jump into our contribution, instead of only systematizing like a survey, different works, we also propose a framework and a set of claims to make some order in the verifiable federated learning area. So that is the big picture of the framework that we can discuss later on in the poster session in the details. And we introduced this set of claims that are 4 claims for client-side verifiability and 3 claims for aggregator-side verifiability. And we say that by implementing these 4 claims, it's possible to achieve an end-to-end verifiable federated learning. Okay, so to show you how our framework can be implemented, there are many different ways our framework can be used. This is just an example, and here specifically for the training. So just to give you an high-level idea, you can see that we can rely on a sort of a tape, a transcript, a bulletin board, we can call it, where the client, first of all, need to commit on the dataset, and later on points 2, 3, and 4, you can see that the training happens, that updates, the ingredients are then encoded, and then you can generate in phase number 4 an evidence to give guarantees of verifiability for what concerns the data usage, the training algorithm that has been used. You can also provide properties of the updates, and uniqueness is needed to avoid replay attacks. And the client later on can publish a tuple with the handle to the gradients and the evidence. And this set of sub E, I've called it, the aggregator can get this set, can verify all the evidences, all the proofs, and can generate an admission set of all the correctly verified evidences. That was for training. For the aggregation, the thing is kind of similar. The aggregator can first of all perform the aggregation, obtaining the theta global, and then can generate an handle to it and the correspondent evidence, and can publish everything on the tape. And later on, the clients, before starting the next round, can verify the correct aggregation. And the tape is needed because also an external auditor in this way can perform a sort of a verification of the entire process. Okay, these are the 13 papers that we systematized, and this is the systematization according to our framework, where VD stands for verifiability of data, VT stands for verifiability of training, and VA stands for verifiability of aggregation. And you can see in the radar plot, looking at the blue shape, that the majority of the work focus on the aggregation, while looking at the dotted shape, you can see the dotted shape indicate the ease of implementation, and you can see that many works don't implement claims that we retain particularly easy and that can get interesting guarantees of verifiability. This is what I've just said. Then moving on, interestingly, many works uses the blockchain as the verifiable tape that I showed in the framework, but mainly to verify zero-knowledge proofs concerning training and aggregation. And this is interesting because a third-party auditor can also check that entities verified proofs before performing his task. Then taking a look on the right side, on the table on the right, you can see, as we said at the beginning, that with verifiability, we can mitigate many attacks. Now I'm not gonna go through all of them, but just focus on the first row. For instance, CL2 is the claim for verifiable training, and with verifiable training, we can mitigate model poisoning, because of course, by stating that you run a specific algorithm, you can sort of mitigate bad behaviors during the training. And by sending the evidence, of course, there is something that you show to a third party, is something that shows that a particular algorithm was run, so you can also avoid free riding. This is what I've just said. Okay, I'm wrapping up. So which are the costs here? On the client side, so for the data, so proving to use specific data and proving certain properties of data, it's nothing else than just a commitment plus a Merkle proof. that's relatively cheap. While for training, the thing is a bit different because you know that there are many non-linear operations that take place during the training in the model, and these are not TEE friendly, and these are not circuit friendly for zero-knowledge proofs. While for the aggregation, these are mostly linear operations that can fit pretty well in a zero-knowledge circuit. So there is a bit of overhead, but everything is implementable in a circuit. Okay, I'm gonna skip this. And to conclude, some remarks. So point number one is that verifiable training was not tackled so much, so we believe that further research is needed. Then point number two, also by our analysis, there are claims that are easily implementable and that can introduce nice properties for verifiability. So we suggest to authors of the work that we systematized to reason on them. Yeah, then we have also seen point number three, that many works rely on the blockchain for verification, but sometimes are really costly. So we suggest to take a look at rollups or modular verification networks like ZK Verify. That's a blockchain meant only to verify zero-knowledge proofs. Point number four, that's for us, we want also to make our claims formal. So we are gonna work on a formalization with some UC style or game-based framework. And to conclude, recently, this concept of collaborative snarks popped up, and basically they give you the possibility to many clients to generate a zero-knowledge proof in common. So this can probably remove the need for an aggregation, but this needs further research. And feel free to connect on LinkedIn and meet me at the poster session.